Another application of spectrophotometry in chemical analysis is the use of spectrophotometric titration. So in spectrophotometric titration, instead of having a standard solution and measuring the absorbance of different known concentration of the standard and creating a calibration curve, then measuring the absorbance of a sample and then use the calibration curve to find the concentration of the sample. We use titration in the same way as we do the titration in the lab, but this time, instead of using an indicator with a change in the color at the endpoint, we will use the spectrophotometry in order to spectrophotometric titration, and we will use the spectrophotometer to determine when the equivalence point is reached. So in order to do this, we need to add the titrant to our unknown solution, concentrated solution, gradually in allicutes of certain volume, and then we need to monitor the change in the absorbance. So as an example, if we have the iron transport protein transferrin, and we need to measure the concentration or calculate the concentration of the transferrin in a sample. How would we do this? First of all, we need the transferrin without iron. It's called apotransferrin and it's colorless, so it doesn't have any absorbance. Then when we add ferric, one molecule of transferrin or apotransferrin will bind to two ions of ferric to make the transferrin ferric complex. This complex is red colored and it has absorbance maximum, or the lambda max of the absorbance of that complex is at 465 nanometer. So what we need to do then to do that, so we need to titrate a solution that has a apotransferrin with a solution or a titrant that contains the ferric ion. So let's say that we have 2 ml of apotransferrin and we titrate this with 1.79 millimolar solution of ferric nitrolo triacetate. This solution will provide us with the iron or the ferric ion that will make a complex with the apotransferrin. What we do is that we start to add the iron solution, standard solution or the titrant in allicutes of 2 microliters or 5 microliters or whatever. So we start to add certain allicutes and we start to measure the absorbance of the colored solution. Once we add the ferric, it will bind with the transferrin or with the apotransferrin and it will make the colored complex and the red color will develop and then we will see absorbance. And then we start to plot the microliters of iron added against the corrected absorbance at 465. What do we mean by corrected absorbance? Um, um, you have to bear in mind that when you add the titrant to your original solution, what happens is that the total volume of the solution will change. That means the concentration will change. So we need to make correction of the absorbance. The correction of absorbance, so the corrected absorbance will equal the total volume over initial volume, and this is multiplied by the observed absorbance. So when you observe, so the absorbance that you get from that solution is not the one that you actually plot in this curve, but you have to use the corrected absorbance. So you need to calculate what is the total volume now and what was the initial volume, and then you multiply this by the observed absorbance. The endpoint here, as you see, the endpoint is when the when you add if when we reach the endpoint, when there is no more apotransferrin, that means no more colored complex will be formed. But if you notice, there is still a slight increase in the absorbance. This is not due to the formation of the colored complex, but this is because the titrant itself, the ferric nitro triacetate, also absorbs at the same wavelengths, which is 465, but the absorbance here is much less than the absorbance of the colored complex, our colored complex. Um, that means that this is the endpoint when you see that the straight line is no longer straight, but it levels off. So this point is our endpoint. So we then find what was the amount of ferric that was added, and then to calculate. So the endpoint here was calculated to be 203 microliter. So the quantity of the ferric required for complete this reaction, as per this figure, was 203 times 10 to the power minus 6 liters times 1.79 times 10 to the power minus 3 mole per liter. So now we can find how many moles exactly were needed from the ferric to get to the endpoint. By multiplying the quantity in liters we added times the molarity of that solution. And you will find that the number of moles are 0.363 millimole. So 0.363 millimole of iron or ferric were enough to react with the whole quantity of apotransferrin. But remember that we said that one apotransferrin will react with two of ferric. That means the quantity of apotransferrin will be half the quantity of ferric. That means the concentration or the quantity of apotransferrin in that solution was half that value, so it's 0.182 millimole. Again, don't forget that we need to account for the dilution when we do our plotting. So, for example, if how would we do this? So, for example, if the observed absorbance was uh, if at certain point was 0.260, and this happened when we added 125 microliter of the ferric solution to the 2 ml of the apotransferrin. How would you calculate the corrected absorbance, the one that you are going to plot? To calculate the corrected absorbance, now you need to add 125 microliter to the 2 milliliter. 125 microliter equals 0.125 milliliter. That means the new volume now is 2.125 mil divided by the original volume, which is 2 mil, and we multiply that by the observed absorbance, which is 0.260. So the corrected absorbance is 0.276. So this is the absorbance that we will plot in our curve, not the observed one. And as we said, we will reach the endpoint when the absorbance